Okay. There we go. All right. Something fun today, I see. Yeah. Since you're all.
Well, first off, welcome everybody. We're talking about something very different than my normal research or anything. It's my, probably my last presentation here. So since I'm about to graduate, so I wanted to just talk about something that I've been interested in lately. That is really cool and fun, and that's arbitrary code execution in the original Pokemon games. So Pokemon Red and Blue version for the Nintendo Game Boy. So here's a quick little outline. First off, what is arbitrary code execution, or commonly called ACE? And then how can we get this glitch item called 8F that will allow us to do arbitrary code execution, and how does that item work? And then all the steps and cool glitches we need to do to break the game to get this item. And then also show you some cool applications of what you can do with ACE. So first off, what is arbitrary code execution? Or ACE? This is a common, really powerful glitch that exists in many different video games that allows you to basically take control of the execution of the game and run custom commands instead of the game's normal code. It can let us turn game data into executable code, and can even allow for the arbitrary reading and writing of RAM while you're playing the game. And so this exists in lots of different games, commonly used in speedruns to complete games really quickly. A really famous example is in Legend of Zelda: Ocarina of Time, where you can beat the game in just a couple minutes. But it requires really clever glitches to figure out how you could do arbitrary code execution. So before getting into it, let me just show you an example of what we can do with ACE in Pokemon. So we're just here standing here. Hold on. Wait, what?
Goes picking.
A little example of ACE in Pokemon Blue version. So we're just standing here. We open up our menu. Look, we have some regular Pokemon in our party. And if we look at our item bag, we have this weird item 8F, and then some regular items. And then some of them have these switch icons. We'll explain that later, but those are regular items. And then when we run 8F, when we exit out of the menu, it triggers an encounter, and the encounter. So you can imagine you made new here. So what actually just happened there? A lot happened behind the scenes. So we started out in this normal game loop, and we used this item 8F, and that caused the execution of the game's code to jump out of that normal game loop and start executing the data where our Pokemon are stored in memory as code, as assembly instructions to the Game Boy. So this series of Pokemon here in this specific order actually is a little program that caused execution to jump out of that and then start executing the data in our item bag as code. And so those items and the specific quantity of these items, that actually was a program that was able to spawn new and trigger that encounter. So how does 8F actually work, this glitch item? Over here, a team called PK Red or PokeRed has decompiled the Game Boy machine code into assembly instructions, so we can actually see what the code would look like as the developers were writing it. We're not going to go through the details of how this assembly code works, but the important part is when any item is used, this function useItem gets called, and that calculates something called the effect pointer for that item, which is basically where the code needs to jump to, what function it needs to call to use that item, to do whatever that item is supposed to do. And so there's this big table called item use pointer table, where each one of the elements of this table is a certain function that gets called, or a pointer to the function that gets called for a specific item. And it's based on the item's ID. Each item has a numerical ID. And this part of code up here calculates, based on that ID, where in that list that item's function pointer is.
And so we can break these down into 2 bytes of memory, and which we call a word. So the first word corresponding to item 1 would be this item useball pointer. And then there are 84 valid items in the game. But this is an 8-bit system. So you can represent numbers up to 255 with 8 bits from 0 to 255. So from 85 onwards are IDs that could correspond to items, but aren't actually used in the game. So these are all called glitched items. So 84 is the last element of this table. But if you have an item that has ID 85, there's actually no check in this code up here to see if that index is in the valid range, 0 to 84 or 1 to 84. So the effect pointer for these glitched items will point beyond this pointer table into erroneous parts of memory, part of this item useball code that is just in memory sequentially directly below that, below this table. And so like there would be word 86, and 8F happens to have ID number 93. And it happens to be that this points to somewhere in the middle of this item useball code. Specifically down here at this 1 byte, or these 2 bytes here that correspond to the address where the number of Pokemon in our party are stored. Address D163. So instead of normally it would, if you use a regular item, it'll grab the effect pointer from this table and then jump execution there to call that function. But for 8F and any other glitched items, it'll point somewhere below that. 8F specifically points to this byte here, which happens to be the address where our Pokemon party is stored. So that's why execution jumps to that location when we use that item. So that means that the game's just going to start executing whatever data are in these addresses in memory as code. It's going to interpret whatever data is here as opcodes for assembly instructions. So that basically means that we can go out and catch certain Pokemon to populate these memory locations. And if we can do it in a clever way, we can write a program by going out and catching certain Pokemon. So here's a big table. We're not going to talk about the details of this, but this is all of the operations that the Game Boy can do, and a big table of the opcodes. So Pidgey, for instance, has ID hex 24. And so if we look at row 2, column 4, Pidgey, as interpreted as a Game Boy instruction, corresponds to that increment H, which basically just, there's a register called H. When you use that function or use that instruction, it increments the H register. So the fundamental thing here is there's no difference between data and instructions. Everything in memory is just bytes. So this is just a little snapshot of some game code, that item useball function, and here's a little snapshot of memory where your items are stored, and they look basically the same. They're just bytes of data. And so in this table on the left-hand side in the left column, you can see the hexadecimal value and how that ID is interpreted in different contexts. So it can represent a certain Pokemon or a certain attack or an item, or in the case we're interested in here, can represent a certain opcode for an assembly instruction. So we saw that 8F is going to jump execution to D163 in memory. And so all of these data onward are going to be executed as code, whatever is stored there. But if we want to do something interesting with arbitrary code execution, we want to be able to modify these data here to basically write a program. And that's very difficult if we're just using the data at this part in memory, because although we can go and catch 6 different Pokemon, a lot of these other data are dependent on each other. Like the Pokemon's type, we can't change. Pokemon have limited movesets. All the stats and the level and the HP and experience of those Pokemon, those are all dependent on each other. So it's going to be very difficult to write a program by catching certain Pokemon, at least a sophisticated program or a complex one. A much better place in memory that we have a lot more freedom to edit and modify ourselves just by playing the game is our item bag. So it's easier to write a program there because items are easy to obtain. Their order can be swapped. We can go and buy and sell or toss items to change the quantities. So it's much easier to modify these values in memory. So what we can do then is use ADAF as a bootstrap. What that means is we can go catch certain Pokemon that'll write a small little program that will, at the end of that program, jump execution to our item bag. And so our party Pokemon that we go out and catch will have to encode a program that jumps to one of these specific addresses in our item bag. And it happens to be that the Pidgey on Tentacle Parasect Kangaskhan, specifically the Pidgey with 233 HP, corresponds to these instructions here that do just that. It jumps execution to actually the third slot of our item bag. And I have set up this whole thing, but we're not going to go through all of it. I guess as I step through this, the important thing is just watching what happens to the registers here. So register is just a thing that stores 1 byte of data. And so as the game starts executing our party Pokemon as code, it's going to modify these registers. So after the H register will change, then the L register will change. And by the end of, when we get to the current HP of our first Pokemon, we've modified these registers to D322. And this last instruction here is a jump HL instruction. What that does is it jumps execution to whatever address is stored in the H and L registers, which is these certain Pokemon have modified that to be D322, and D322 happens to be the third slot in our item bag. So this series of Pokemon, and specifically the Pidgey with 233 HP, do exactly what we wanted to do, jump execution to our item bag. So how did we trigger that Mew encounter? We had a specific set of items that basically did whatever we needed it to do to trigger that encounter. So basically what we need to do with our items is set them up in a way that it'll load Mew's ID into this specific address, D059, which stores the current Pokemon or current opponent. As in the normal game loop, the game will check this address in memory, and if there's an ID of a Pokemon set there, then it will trigger an encounter. So if we go out and we get 21 lemonades, it will load hex 15 into the A register. If we get 89 X accuracies, it'll load 59 into the L register. 208 Carbos will load D0 into the H register. Pokeball, that doesn't actually matter, but the quantity of it corresponds to load A into HL. So that'll store that value 15 at HL, which we've set to D059. So that's exactly what we intended to do here. We've set Mew's ID into that specific address. And fresh water doesn't do anything important, but then the quantity of that corresponds to return. So that'll jump out of the item menu function that we used when we used ADAS. So you'll notice that we have large quantities of items here, 201, 119, etc. Normally in the game, you can only get 99 items. So how do we get over 99 items? This is a little bit more in depth than we have time to go into, but you can use something called the Missing No glitch, which is probably the most famous of the first generation Pokemon game glitches. But we can talk about how to do it. It's the simplest thing. I remember doing this as a kid when I was 9 years old or something. You go talk to this old man in Viridian City. You immediately fly to Cinnabar Island, surf on the East Coast here, and you have a chance to encounter this glitch Pokemon, Missing No. Maybe you've seen this image before. And a side effect of encountering Missing No is it adds 128 to the item in your 6th item slot. So if you need more than 128, you can toss one or toss some, go encounter Missing No again to get up to 255, and then toss however many you need to get the correct items for whatever opcode you need for your assembly instruction. So since since the game is only coded to let you get 99 items, these tiles here that are displaying the number of items, they get glitched out when you go above 99. And so it'll just display some other tile as part of the tile set that just corresponds to a number greater than 99. So how do we actually get 8F? I have a video to show this, so I'm just going to skip through this and then play the video.
Okay,
Hopefully.
now I'm going to show you how to use something called the item underflow glitch to explore memory in our item bag beyond where we're normally allowed to. So first off, what we are going to try to do is underflow the quantity of items in our item bag. So at D31D,
So by that, I mean, each byte in memory is 8 bits, which means we can, like I said, we can represent numbers from 0 to 255. This location here, D31D, that stores the total number of items in our bag. It's an unsigned integer. And these quantities are unsigned integers. So if we, by underflow, I mean, like if we subtract 1 from 0, it'll underflow and wrap around to 255.
the number of items in our item bag, the number of item slots used. And that's highlighted here in red in the memory viewer, D31D. So it's at 3 right now because we have the master ball, the ultra ball, and the X special. Now, if we delete the master ball, something interesting is going to happen. We will delete it. It's going to decrease that number to 2 right here. Now, it did something else interesting. It duplicated the X special. Basically, that happens because there's 255 X specials here. That's what that blue bar 5 means. And the cancel button actually has the ID of 255. And so when it's reading through the list to copy the items up, it gets to the quantity 255. It thinks it's reached the cancel button, so it stops the copying process prematurely, and ends up duplicating the X specials. So we can do that again. Now watch the red quantity in the hex editor. It will decrease from 2 to 1 as we've gotten rid of that ultra ball. Now, of course, it still looks like we have 3 items, but the game thinks that we only have 1. Now we can do something kind of similar. If we toss 253 of the X specials and then combine these 2 stacks together by swapping them, what it'll do is it'll try to add the quantities together. 255 plus 2 will overflow to 1. Oops, swap them. And it's decreased our number of items in our bag, that highlighted red quantity again. Now it's at 0. Now, if we swap these, again, the quantities will overflow. 255 plus 1 is 0, but it's going to decrease the number of items in our bag again, and it'll underflow from 0 to FF, which is 255. So now we can actually scroll down past the cancel button, and it thinks that we have 255 items in our bag. And so we can go and let me move the hex editor out of the way. We can go and look, scroll through past all 20 of our items into other spots in memory, like the money, our rival's name, miscellaneous options. And specifically, we want to go look at the current player's X position, because what we can do now is if we go to the edge of Celadon City here, normally if we take one more step, it'll increase our position.
Just say one thing first before going into this. The idea here, remember, the whole idea here is we're trying to get that item 8F. And so 8F has a certain ID, 5D and hex. And if we can get our player's X position to be that ID, if we can move to location 5D or 93 in decimal, then we could just scroll down to this location and then that item will just appear in our item bag. But normally you can't go 93 tiles in one map. It'll start loading the next map. So basically what we have to do is use a glitch to basically get out of bounds so we can move far enough in the X direction to get to that location.
And it'll hit a loading trigger and load the next map. But let's just go see what that looks like a little bit. You can see all of that there. Now, if we take the X, so one second, we're at location 33, I think. That's our player's X position. if we go here and we take our X special, we copy it, we select it, and we go down all the way in memory to where our player's X position is. Right now we're just scrolling through memory beyond where our item bag is. And we're going to have to go for a while. It's going to take a little bit. And occasionally it kind of gets stuck where you have to press A due to some 8 here. I happen to know that this nugget is representing our player's X position. Now, if we remember, we're still holding that X special. Now, if we swap it, what it's done is it's swapped the nugget with our X special. The ID of our X special, which is something like 44, is now stored in our player's X position here. Our player's X position. Now we are at location 33. 44 is greater than 33, so it thinks we're at location 33, but we actually haven't moved on the map. And so it's jumped over that loading trigger. Now you can see the map is all glitched, and we can walk into this big open space here. And if we look at our items again, see this is displaying our current player's X position. It says something like B1F, that's the ID for a different item. We take another step forward. Now it's increased 1F, one more step, 2F, and now we can, since we have this big open space, we can walk to where 8F will be. So that's 4F, 5F, 6F, 7F, 8F. And now here's 8F. And we can select it and swap it back to the top of our item bag so it's in our actual item bag, and then we can use it like a regular item. So that's how you get 8F. Now, interestingly, I think if we just use it now, it'll probably crash the game. Yep. But anyway, that's how you get 8F.
Yeah, essentially we just needed to be able to walk far enough to get that, to get our X position equal to the ID of 8F. And so you couldn't really see it because it only shows a certain part of the map, but this is the whole map, and we were on the edge here, and when we walked farther by going out of bounds, it actually just kind of loaded all these tiles are stored in a 2D array, but flattened into 1D in memory. And so when we walked farther, it just loaded the next part of memory, which is down here. So it just kind of periodic boundary condition looped around. And we specifically just needed it to do it here. There's probably other places in the game you could do it, but this gives us this big open space where we can walk really far in the X direction. Okay, so that's how we get 8F. We saw what actually happens when you use 8F. When you use 8F, it jumps the game's execution out of the normal game loop, starts executing the data where our Pokemon are stored as code. You catch certain Pokemon, specifically this list here, that is a little program that will jump execution then to whatever we've programmed into our item bag by getting certain items and quantities. And then, we can basically just write an arbitrary program in our item bag. So that's how 8F works. And last, I'll just show you one cool example of kind of the more advanced thing you can do with 8F.
Okay, now for the coolest use of 8F that I've ever seen. So if we look in our item bag, we have 8F and then Carbus, X accuracy, and TM33 with certain quantities. This is a little program that will actually jump execution to our PC, specifically where our items are stored. And if we look at where our items in our PC, we have big list.
So this is another level of bootstrapping. We've jumped execution from our Pokemon to our item bag, and now from our item bag to the items that are stored in our PC.
Here, this is a
Because you can store more items in your PC than you can in your item bag.
program with some glitched items and quantities greater than 99. So they have this glitch icon as the quantity. So this is the program that'll get run when we use 8F. So let's see what that does. We'll use 8F, and it doesn't look like a whole lot happened, but up at the top here, it shows an address, D86B, and a value. This is actually a memory writer. So we can press up to increment the byte and left to shift it, multiply by 2, and then right to enter that.
But just to be clear, the code that's in the item in our PC, it's everything that's necessary to handle the user input from the Game Boy controls to display those digits, to display those tiles on the screen, to send them to VRAM, everything that's all in that code from the items.
Right. and advance to the next address. So we can just manually, arbitrarily write data to RAM and do anything with that. Now, it's very slow to write it all by hand. So I've written this script in Lua that will just automatically simulate the joypad inputs to control that RAM writer. These are just, simulating the Game Boy inputs up, down, left, right in the emulator BizHawk that this game's running in. So if we run 8F and then run this script, then it'll just start manually or automatically entering in this payload that we have programmed up here. So all of these bytes, a few hundred of them. So this is going to take a little while. But so we saw that it started at D86B. That actually is a little bit before where wild Pokemon are stored in RAM. And so it's just going to write this payload from that value onward through our wild Pokemon, through the opponent's trainer's Pokemon, down past some etc. things, game time, and then into the stored Pokemon that are stored in our PC. And so this is all free space that we just have to freely edit, as long as we don't care about any of these data here. We don't want to go beyond these Pokemon in our PC because that gets into the internal data in HRAM, where if we modify that, it might break the game, might crash it, but we don't need to go farther than that with just this small payload here. So this is going to take a little while, so we'll just fast forward and because it's basically entering in 1 byte per frame, or 1 byte every 2 frames. So hundreds of bytes takes a little while. Okay, so it just finished. Now, if we use 8F again, it's just going to bring up this RAM writer. So what we need to do is change the quantities of these items, the carbus and the X accuracy, so it'll jump execution to D86B, where we wrote that program. So we could do that by tossing some items to get their correct quantities and maybe using missingno to get more quantity, but just for the sake of time, we'll just manually edit it in the hex editor. So these items are stored at D322. So right now it's pointing to D53B. We need it to point to D8 6B. And there we go. So it doesn't look like the quantities changed, but if we open our item bag, you can see the different quantities now. So here we go. Let's see what happens when we run 8F. And there is a little message. Hello, Computational Cosmology Group. And if I press right, it starts a little mini game, little brick breaker style Pong kind of game where we just bounce this ball around. But the amazing thing is this is programmed completely natively within Pokemon. This is like video game Inception. We're playing a game inside a game. This was all just done with inputs to the game using glitched items and catching certain Pokemon. Just by playing the game, we were able to take complete control of the Game Boy hardware, write out a message at the beginning there, and then program this whole little game. So I think it's just amazing that people have figured out how to do this. This Pong game wasn't written by myself, but I just used the code that a guy named ZZAZZ wrote. But yeah, this is just one of the beauties of Pokemon, and the amazing work that has been done to find these glitches and take control of the hardware with arbitrary code execution. So that's about it. And yeah, that's pretty much it. So, yeah, any questions?
So would I be correct in saying that one of the most important parts of this is that it didn't check the index in the initial table?
Exactly.
Do games these days check that sort of index or?
Yeah, probably. I think a lot of games now are a little bit more careful about how their data is used. I think there's a lot of oversights in these old games just because of the limited amount of space you have to write your code, a limited amount of memory, which I think is why there's a lot of glitches in older games more so. So yeah. But yeah, you are right. That is if it would have checked if the ID was between 0 and 84, then yeah, none of those glitched items would do anything.
So yeah, there are actually, tons of other glitch items that all have different effect pointers that jump to different places in memory, that some other ones can be used for ace and some others just break the game. And
What's stored in the byte stream? I mean, I'm trying to figure out like.
yeah,
what was-
so
I see a lot of repeating, 77.
yeah, this was a simple way for me to write out those characters. So this is the first part of this program, all that stuff with the 77s.
Yeah.
That's the code to load a byte into VRAM.
Okay.
So it's like loads the address, it sets the address of the tile in VRAM, or the spot in VRAM where a tile will be displayed. And then loads a certain byte into that address. So it just does that for all of the characters. Hello, Computational Cosmology Group. And then the rest of it is, let me see if I can get out of this. And I think if I just type in paste bin, because I've looked at this so much, this is the code for that Pong program. Let me. So yeah, I didn't write this, but this guy ZZAZZ wrote all this. And then I think I don't know if he used a compiler or by hand translated these assembly instructions to opcodes. So everything else in this right here is just the opcodes for those assembly instructions for corresponding to this code here. Yeah. Yep. Any other questions?
And you never actually had to modify game code, technically.
Right,
like you never
no,
had to
I didn't have to like recompile the
Yeah,
game or
that's
anything.
cool. No, when you first started, I was like, oh, there's probably like one point where you have to modify the game's code and then it works. But
So
it's all just through actions within the game.
Right, exactly. That's the really cool part about it. So I've actually used this in real life on an actual, well, on the virtual Nintendo DS, like virtual console. But it works just as well as the emulator as the original hardware. But on my Nintendo DS, I went and did all those steps to get ADAF, set up the party Pokemon like that, set up a certain item list to be able to catch Mew and then make it shiny, and then make it have the original trainer ID, that the original distribution event that Game Freak did back, that you can't really get shiny Mew anymore, but so you can use ADAP to change the ID of the trainer ID and the stats to make it shiny, and then make it like legal to transfer it up into Pokemon Home. So yeah.
You know, this was figured out before, like without emulator, or?
I don't know. I think it was
I don't think.
about 10. I know there are forum posts from like 10 years ago,
Okay.
12 years ago, or something like that.
It's been around. I mean, when I was like in school,
Mhm.
when I was playing.
Yeah,
2000.
Yeah, it came out in
I used emulators.
1999, I think. So,
Yeah.
yeah, I think this was probably discovered after emulators, once people decompiled the code and everything. But I'm not sure.
Yeah, it was done like 10, 15 years ago, even like 20 years ago.
Mm-hmm.
I did it all on emulators.
Yeah. All right.
Yeah.
Thanks, everyone.